سجل. Good morning everybody, welcome back to lecture, good afternoon everybody, welcome back to lecture number 2. Today I will go over the course again because I wanted to show you an interesting update in the slides. So last time I told you that in this course, yes, we will be studying the motors themselves in a more detailed fashion, but we will focus into other aspects. What are the loads? In 360, we never mentioned what are the loads. Did we model the loads? We did not. Have you ever dealt with Newton meter apart from the electrical part? No. So we probably need to model the loads a little bit, such as the inertia constant, etc. We will also study the feedback signal. We have to get some measurements from the motor. Otherwise, how can you update the controller without knowing the speed of the motor, without knowing the torque in the shaft, without knowing how much current is flowing? We will look at the control aspect. Pulse width modulation, PWM, and even basic controllers. For example, we can change the voltage. We can change the frequency of the machine. We can come up with different shapes and design to match the desired load. Don't forget, we always have a control reference. A control reference, that a set point that the controller, which is usually Arduino or microprocessor, etc., that will update the values of the voltage or the current or the frequency applied to the machines itself. Okay? So what are the major components? We have a power source, we have motor, we have power processing unit, electronic converter. For example, we have MOSFETs, anything from 303. Okay? Anybody is taking industrial electronics? Okay, probably you will study many of the high voltage power electronics, okay? Thyristor. In 360, the last semester, we introduced a small module in power electronics. And I know all of you, anybody if you took 360 last semester, it's impossible, because you have to take 380. So the idea about it is take 303 devices, apply them to bigger scale, then you have the power processing units. Big diodes, big transistors, big MOSFETs, big IGBT, etc. Okay? There are two types of control. You remember from 380. We have open loop. We have what? Closed loop. Which one is usually better? Closed loop. For what purposes? For feedback and stability. We will tend to have a more stable controller if and only if it's in a closed loop manner. Okay? Take, for example, this block diagram. And we will see in this course lots of block diagrams. No need to memorize them, but try to understand them. Because if you understand them, you will be able to explain every component. Okay? I might ask you in the exam, what is ASD? Any guess? Okay, let's start with
adjustable speed drive.
That's correct. Thank you. It's an adjustable speed drive. We can adjust the speed of the motor. So when you look at the application, look at the load first. What is the load? It's mechanical load. It's HVAC unit, air conditioner, okay. And the sensors, where are they? In the back. We want to control the building room temperature, okay? If the room temperature if the room is hot, we want to push more air in the system, okay? So the sensors would send back to the system controller. We have a temperature reference. We have a temperature reference, and then it will supply using frequency, the pulse width modulator, and then it goes to the diode, and then it runs the motor using 3 phases. But this looks like a closed loop, صح?
Yes.
But is it a closed loop from control aspect or from machine's aspect? Look at this block diagram. Yeah, we have sensors, but what are those sensors? Temperature. I don't care about the temperature in my machine because it doesn't, the closed loop has to do with the building temperature. It has nothing to do with the machine itself. So that's why I'm calling it open loop control of the drives. Yeah, it's a closed loop in terms of simple room temperature, but we're not control engineers, we're machines. Let me explain it one more time. We're getting temperature, humidity from the building for the load, which is air conditioner. We're using only temperature and humidity to drive our machine. What if the machine electric current is too high? Do we have a closed loop in the machine electric current? What if the magnetic flux is too low to drive the load? Do we have such information? That's why it's an open loop. Yeah, there is minor controllers, maybe even there is light sensor, you can add whatever you want. But these controllers are not machine control, are not drives. Look at the closed loop control. This is good stuff. Why it's good stuff? Because I'm not dictating on my machine the load. I'm not gonna let the load control my machine. The room temperature made our machine spinning, correct? The load, the room, the control signal drove our machine. Is this what we want? No, we don't want that. We want our drive for the motor to be based on the motor measurements itself. So here we're measuring speed, we're measuring current, 3-phase, we're measuring voltage, 3-phase. So we're getting ABC, and then the speed. Maybe sometimes we measure the torque in more complicated control scheme. And then what am I doing? I'm measuring the speed, feeding it to the speed regulator, and I have a reference signal. I want my fans not to exceed 500 RPM. Yeah, now I'm measuring things that are related to the motor itself, not the load. I'm not going to let the load dictate how I control my machine. And then I take T reference, which is a torque reference, to control the speed. Speed times torque is power. So if I deviate on the speed, I have to increase the torque a little bit. So this is torque reference signal. I add it to another block. We will learn more about it later. It's torque and the flux regulator. The purpose from this block is I give it a reference flux, I give it a reference torque, and then I get a reference current. Because if I know I need a huge torque, I need a huge current. But of course, electric machines, they may saturate. We may have a certain limit on the current. If we exceed this current on the machine, we will have a problem. We might burn the machine. So there is lots of constraints. Yeah, I can have infinity torque, but can I have infinity current? No. And remember in the transformers, we reach the saturation. Do you remember the BH curve? We don't want to saturate our machines because the idea of saturating your machine is you put more current, but you get limited flux. You don't get much flux because you're at the saturation. You always run at the corner, the knee. We got the control signal. We have a current regulator. So the current regulator, we get the voltage, we get the current. Of course, in the torque and flux regulator, you also get the speed. You don't have to memorize these details, but understand the concept. The current regulator tells us a voltage. This voltage will go to the power electronics, which is switch control signal, generator, pulse width modulator, and then we get the control signal to the power electronics, the diodes, the IGBTs, the MOSFETs, the rectifier, the DC link. All of these things are electric circuits that we send the control signal to get the desired voltage and current. The moment I get the desired voltage and current, I'm going to get the speed. But one student might ask, okay, what if the load gets heavier? If the load gets heavier, the speed most likely would be decreasing. It's going to deviate from the speed reference. So I'm going to have a signal. I'm going to have firing commands across this chain all the way to the power electronics. Get it?
Yeah.
So that's the idea of closed loop motor drive system. It's not temperature is cold, spin the machine faster. No. It has to you have to dive into the characteristics of your machine. How much voltage, how much current. More advanced models, they even look at how many rotations the rotor spins. Some they look at the magnetic flux inside the machine. These are more advanced level of the control. Why am I saying that? Take for example the electric vehicle. If you have an electric vehicle, do you want to allow the driver just to control the speed based on his vision or her vision, or based on the self-driving mode for the Tesla vehicle? Do you want the car to dictate how the motor is spinning? Or it's better to get an informed, more data, and then we can control the motor properly. So if you drive the car, you're giving the speed reference, right? But can you give the torque reference? Can you give the flux reference? No. This is what we're gonna learn in this course. So yeah, we know how a synchronous machine works. We know how an induction machine works. We know how a DC motor works. But in this course, we will dive into that aspect. And I don't think it's hard, but I think it's very useful. Okay? I don't think it's hard, but I think it's very useful. And I believe the Machines Lab is very popular, correct? So hopefully, you don't have to take it, but if you're taking it, probably you're going to have both knowledge, more practical, Dr. Wali and Dr. Muhammad Atta, صح? We have 3 sections. Hopefully, these two will supplement each other, but it's not prerequisite, so you don't have to take the course to take the lab. Some people taking just the lab. Okay? And last time I told you, these are the types of the machine. We will cover synchronous, induction, DC. At the end, we'll talk about universal and stepper motor. But again, I'm not going to teach you how those machines work, rather how to control these machines. Okay? So, any question about the introductory module?
So,
yes.
The DC motors, are they of use today?
To the best of my knowledge, they are still used in trains, in electric trains, metros, due to high torque that they have. But in electric vehicles, they are not used. In electric vehicles, to the best of my knowledge, 2 types of machines: induction machine and permanent magnet synchronous machine. Why? Because those 2 machines, an induction machine with permanent magnet synchronous machine, they can run as a motor and as a generator. If you're driving your vehicle up, you need it in a motoring mode. If you're driving your vehicle down, we have what we call regenerative braking. This regenerative braking, the permanent magnet motor, now it becomes permanent magnet generator, and the induction motor will become an induction generator, will run as a generator and it will charge the battery. So that you don't need to consume all the battery levels. Anybody is driving a hybrid vehicle? So I do have a hybrid vehicle. Usually you get the double mileage because of this regenerative braking. Some people, they even, probably you know it or not, but there are people who are challenging themselves to get the highest mileage for their hybrid vehicle. So they tend to drive in an interesting manner. They try not to press speed control. Their idea is to make the EV motors to run as much generators as possible. This will extend the life cycle of your machine. But why permanent magnet? Why permanent magnet synchronous machine? Why not the regular one? For a thing that we will study. Permanent magnet synchronous machines, they give you the electric field in the stator, the magnetic field. Correct? Other type, you don't have a permanent magnet, you have to supply it yourself. So can you supply three-phase magnetic field in your synchronous machine all the time? In an electric vehicle? No. But how about a generator in a power plant? Yes, you can excite it, you have auxiliary. We will study how to excite synchronous generators either today or Thursday. Okay? Any other question about the introductory module? So question in the test. This is a closed loop. This is a closed loop control of drive. False. Why? Because we're using information in the controller that are irrelevant to the motor. They're more about the load. Okay? So when you go in industry and you see a generator or you see a motor, always ask yourself, where is my data? Where is my current sensor? Where is my voltage sensor? Where is my tachometer? Where is my torque meter? Okay? This is very important. Okay, any question? So if you go again to the drive, I'm going to put everything here, homework, solutions, quizzes, etc. I will populate them all the time. Module 1. So this is just a review of electromechanical energy conversion principle. This is basically from 360. I'm not going to ask you more about it. It's just to refresh your mind if you took 360 more than probably 1 year ago. So let's look at the basic principle. Induced voltage on a conductor moving in a magnetic field. So this is the magnetic field in this drawing, okay? What is the direction of my magnetic flux? Is it into the page or out of the page? Into the page. Why? Because I have the X. If you have the dot, it's out of the page. I'm moving my cable that has electric current, okay? No, let's say it doesn't have electric current. I'm moving my cable across the magnetic field using speed. I'm going to have an induced voltage according to this polarity. Now, if I have now, myself, I'm pushing this cable, this wire, in a magnetic field using velocity v in a field that is into the page. So I'm going to have an induced voltage. The direction of the polarity uses the right-hand rule, okay? Using this formula. A wire moving through a magnetic field experienced induced voltage across its terminal. Using this formula, the speed times the flux times the length of the wire. These are the information, velocity, magnetic flux, L. So the polarity is such that the positive terminal is in the direction of the vector V times B. If you use the right-hand rule, I'm not going to ask you to do it, but get this into your mind. So now we are generating voltage in the cable. The other thing is, can I produce a force that moves into that velocity if I have a wire that is carrying current? This is the motoring action. I have a wire that has the current moving from top to bottom of length L. because the current is moving into the wire in a magnetic field. This magnetic field is uniform. It's not AC, it's uniform. Then the wire itself would experience a force into this direction. If I reverse the direction of the current, or I reverse the direction of the flux, the force will be the other way. As an engineer, you really don't need to know this rule because we have simulation tools. The most famous one is ANSYS electronic desktop. Okay? In this course, we're here to learn, okay? We might explore some of those FEA. It may be one or two homework, just to see how magnetic flux and the forces and the torques interact. So I'll try to secure a software, find a good software for you. I believe ANSYS has a student trial version. Try to download it yourself, but there is also other software that simulate the machine, okay? So the direction of the force again is using the right-hand rule in a motoring action. So one of the conditions for your electric motor to drive is you need to have a field and you need to have current through your conductors. If those two conditions are satisfied, you will be able to generate a force. And this force would lead to the rotation of the machine. Either way, generating this magnetic field is a job by itself, is a requirement by itself for generator or for motor. You really need to have a uniform magnetic field around your conductors. Recall again, we usually have the stator as the outer fan, the rotor is the inner cylindrical or salient pole. These are two examples. Usually, the shaft is connected to the stator. Now, there is other machines where the stator is inside, the outside is the rotor. But let's focus on the majority of the machines. The majority of the machines, I hope you still remember that the stator is the part that is external. We usually have it externally such that we can generate magnetic field in the case of synchronous and induction machine. For the case of DC machine, it's the armature where we induce the voltage value. Again, in this course, let's stop calling it motor generator. Let's just call it machine, okay? Why? Because now I have enough knowledge to tell myself, okay, am I operating at a motor mode or at a generator mode? Think about the EV. In the electric vehicle, they name it as motor because the public audience think, oh, it's a motor. Because if you tell them that's a generator, they probably won't buy the car. But the actual technical name for traction systems, the engineers, they just call it the machine. And based on the controller, you're either operating at a motoring mode or a generator mode. So that's the important thing about machine. Now, you get other cases like the wind turbine. We always run the induction as a generator mode, correct? Or get the regular power plant synchronous generators. We always run them as synchronous generators. But now, with the advances in power electronics, take for example SVR, static variable reactor. The SVRs, for example, they might run as motor or generator. So it's better for you as an engineer to protect yourself just to call it as machine. Okay? Call it as a machine because you really don't know, are you operating at a motoring mode or a generator mode? And when you develop the equivalent circuit, based on the operating mode, you just reverse the direction of the current. Okay? So the component and construction details of the motors and generators are the same because the machine itself is a motor or a generator. So part of your controller, you always have to make a decision. Are you running as a motor or as a generator? And as you know, you're familiar with the power losses. we always get the losses if you convert from one form to another. You always get losses. As a matter of fact, one of the biggest losses that we are experiencing as an engineers tend to be where? Tend to be at this power electronic converter, because it consumes so much energy. Think about it as to generate the pulse width modulator, to drive those power electronics, you're losing so much of your energy into those adjustable speed drive, ASDs. The whole component is ASD. The whole component here is ASD. And what is our favorite equation? Angular speed times torque is volt times current. This is how you assign what's the torque needed if you have, what's the torque generated if you have this VNI. And if you have this needed torque or this needed speed, how much VNI you need. This is the fundamental of equation of electric machines. You always need to remember this. Power is usually angular speed times the torque equals voltage times the current. And in 360, was the voltage RMS, or was it peak, or was it real time? We did with RMS. But do you think RMS is useful in the transient state? You're just operating your machine. Would RMS be very useful? No. RMS is useful only in the steady state. So now we really need to have real-time expression for V, real-time domain expression of I, real-time domain of the torque, real-time domain of the speed across the time. In the transient analysis, the moment you spin your machine or turn it on into the system, you have to deal with the transient. Not only that, if your generator is out of service, the neighboring generator would experience transient effect. If you have decided to turn off 3 wind turbines out of the, how much in Domet al-Jandal? 99. 2 of them now are out of service. This as of December 31st. So maybe they fixed it. And by the way, the owner of, I think the Aqua Power is owning one of them. The other one is owned by 3 different companies. حق Domet al-Jandal. It's very interesting. Try to visit it. I think I had so much fun here. بعدين كان فيها one of the things I remember. I'll probably share. Remind me to share the photo. كان في قلعة أثرية وراها نخل وراها على الهضبة. طبعا هم حطوا دومة الجندل على هضبة وراها الويند تورباينز ال 99. So this view was probably one of the best views يعني في سكاكر دومة الجندل. So how to generate the voltage? Well, do you want the motor to move linearly all the time? No. We tend to prefer rotational movement because it's easier to contain, smoother, and it gives you the same torque. You can use mechanical engineering gearboxes. وش يسمونه هذا حق السيارة؟
وشو؟ shaft.
Shaft. لا the one that converts the movement. Axis. Differentiator. You can do magic with mechanical engineering. As long as you have a torque, they can do whatever movement you want. But from electric machines of point of view, we really need to have the windings in this shape, in a cylindrical shape, to get the force, one force up, one force down. So what's the result? Spin. So this is a common question. Why we have cylindrical electric machines? Does it because we love rotational torque? No. It's because from magnetic field or magnetic force perspective, it's better to have the forces one acting across the other direction so that you get the spinning movement. It's better to have this shape than a linear shape. You effectively even increase the length, the active length L, you have 2L. So it is known that if coil is rotated in a magnetic field, a voltage is induced. So coils are better than cables. And what's the best way to form a coil? In a cylindrical structure. This is the equation of the flux, and you note that with respect, if you draw yourself here, if you're walking across this, the coil will spin, صح? Because the coil is spinning, every time you spin, you see different flux. So if the coil is this way, you see a flux. If it's this way, you see another flux. The coil is this way, you see a different flux. So we have a time varying flux based on omega, which is the angular speed of your coil. The maximum flux, which is the one that we use in 360 theta, is actually B times A, the area of the coil times the actual flux that is uniform, the DC flux. And omega is 2 pi f, A is D times L, theta n is BA. And we remember also, by Faraday's law, the voltage induced is given by this equation. The voltage induced is also AC. So question, in the DC machine, do you remember in the DC machine, what was the voltage in the coil? Was it DC or AC?
The coil?
In the DC motor,
DC.
wrong. It was not DC. Inside the coil, the voltage was not DC. Because of the commutator, it looked like a DC from the terminal. But the actual induced voltage على الcoil, it was AC. Doesn't make sense?
I think the two terminals in DC were like synchronized such that the output is...
Yeah, the terminals, عندنا commutator. What's the job of the commutator? To make sure that the terminal voltage is always connected to DC. But an induced voltage, طبعا a DC motor, you put DC, actual DC. There is additional, you put DC, صح?
على الستيتر على الأرض.
Yeah, على الكويل كله.
Okay.
يعني here you have positive negative terminal. Because it's spinning, the aim of the commutator is to block the induced AC voltage due to the rotation. في عندك two components في الكويل. Induced voltage because of the rotation is DC. But ما هو في صالحك تطلعه في التيرمينالز حقت. That's why here you have هذه الكوميتاتور اللي هي carbon brushes. You look at from outside the brushes, it looks like a DC because you're supplying DC. For DC generator, you're getting DC. But it induced due to the rotation, it looks like there is an AC component. فالAC وراك يعني ما ينفع to ignore it. Why it is important to know that we have a DC? Now we have to control. If I want to control the DC machine, I have to control the flux. It's very important to control the flux, okay? Again, these are from 360, not telling you something new. هذه سلايدات دكتور مهيني. He's one of the great scholars who's teaching machines and power. Anybody took course with Dr. Mheni? So these are his slides. I actually think his slides are one of the best slides. Now, looking at it, by Faraday's law, you get the RMS value, get the RMS, take the amplitude, divide it by square root of 2, take the derivative of the sign, there's omega that comes from the derivative. I am very weak in math. I always tell the students that the toughest course I took was Math 002. I will never forget it. So this is from Math 002. Trigonometrics is Math 002. Also Math 102 was very difficult. The idea here is you get this magic number 4.44 times the flux times n, which is number of turns, times the frequency. This is the frequency of how many times your machine is spinning, the speed. It turned out that the induced voltage is measured using this quantity with K, which has to do with number of conductors times number of poles over number of current paths. Basically, this is the geometry of the machine. So changing the geometry of the machine, you can change the constant of the machine. We all remember our favorite equation, omega times torque is voltage times current. We know that the induced voltage is this flux constant times the speed. This is for a DC machine, for example. Then you can get the torque. You either change the geometry of the machine, or you either change the flux, or you either change the current to change the torque. Can I change the geometry of the machine? Can I change the number of poles? It's too much. So I only have to change either the flux or the current. Look at this block diagram. We are changing flux, we're changing current. So the machine torque is a function of magnetic flux and current drawn by the machine. Two things at a time. If the torque is too high, does it mean that current is high? Only if I fix the flux. Maybe the flux that went up. Maybe both of them went up. So it's a multi-disciplinary area. An electric machine, the beauty of it is you learn electromagnetism. You learn power electronics. You learn control. You learn electrical, like power. You learn thermal. You learn mechanical. Too many aspects. And if you work in a team, are you familiar with the company SEER? SEER is a new company that its aim is to go into EV industry. يعني بدل ما نعتمد على لوسيد وتسلا, there's a tendency. Manufacturing electric vehicle is not a magic. In my opinion, it's much easier than regular cars. عشان ما في combustion وما في. I think it's too easy to manufacture. But the problem with it is getting the batteries and the control aspect. These are technologies that they usually buy as a bulk model. Do you think Tesla manufactured the induction or permanent magnet machine? No, they buy it from China. What Tesla is doing, they design their own drive. فنانين, the drive they're doing very good. But it doesn't matter, they get whatever machine they have. But in the drive, they implement their technologies. A self-driving car, if you integrate it with this, that's what they are doing. Rather than having a speed reference by the user, the self-driving vehicle gives the command to the drive. So the drive is the heart of your EV. And learning how drives work or having some exposure to drive is a very valuable skill. Highest paid power engineers in the US are power electronics engineers as well as the drives engineers. It's not the protection, because there is so much lack into this area. And in the kingdom, if you open a company that manufactures drives, nobody is competing with you. You're just competing with usually Chinese manufacturers. But I think in the kingdom there is one or two companies that manufacture motors. We have companies that manufacture شركة محولات, they manufacture transformers. But I'm not familiar with a company that designs inverters or manufacture drives for traction applications. Okay. We have a few minutes left. So this is these two equations form the basics of electromechanical energy conversion. Practically, machines are different. We have voltages generated in coils with multiple turns. We have coils rotating in a magnetic field. Sometimes we have rotating magnetic field. Sometimes we have a DC, AC, etc. Many coils are connected to form the armature winding. What's the armature winding? The armature winding is the winding that produces the magnetic flux, that induces the flux. The flux is produced either from permanent magnet or or from electromagnetic circuit. Electromagnetic supply through a number of coils, such as the field winding. So one important concept, in summary, electric machine shall have two important components, the armature winding and the field winding. The armature winding is a winding in which the voltage is induced. The field winding is winding through which current is passed to produce the primary flux. هذا definition. The synchronous generator, a rotor is the armature or the field? The field. Why? لأن الروtor is one that's producing the main flux. The DC machine is the opposite. The DC machine, the stator is the field winding, or rotor is the armature winding, because an induction occurs in the rotor. Okay? We'll talk about it later. But I am pretty sure that, including myself, we all forgot 360 details. صح?
Yes.
We forgot. So I thought this lecture is a good idea to catch up. Now, I am not going to explain synchronous machine. I'm not going to explain DC machine. I'm not going to explain induction machine. You have the YouTube channel. Go over the 1 or 2 lectures. The first 1 or 2 lectures for every machine is more than enough. If you want the slides for E360, I can share with you the link. But to try to brush up your mind with, for now, synchronous machines, okay? What do I want you to study this week? Synchronous machine. Why? Because the next lecture, we will start about module number 2, which is synchronous machine. How we control them. So I want you to study. So here, boom, we jump directly at excitation. How can I explain excitation if you don't know how the synchronous machine works? So please, optional homework, watch the YouTube videos about synchronous machines. It will take you probably an hour or 2. Speed 1.5 is probably enough. If you want the slides, send me Teams, I will share with you the link, or I put the link in the OneDrive. I can just put one link, you can see all the material for 360. But next lecture we will start here. Please, brush up your mind with what? Synchronous machines. Okay? Clear?
Your YouTube channel, that's all.
It's the same. Okay?
There is a playlist for synchronous machines.
Yes. No, there is for 360, but you go through the titles
Mm.
until you find synchronous.
Mm.
Okay? You don't need to watch everything. You can skip examples or details, just the first few lectures. Okay? Also watch some other YouTube animation, how synchronous machines work. Should be more than enough. So, attendance, I will stop the recording. Any question before I stop the recording?